Okay, welcome everybody. Today is Thursday, so before you hit the wrong weekend, we're gonna have a 3-day weekend, right? So let's just take a look at updates. So Monday next week, there's no class. Of course, I don't have to tell you that kind of stuff. You already know, but Monday, no class. So Tuesday, 9 a.m. Tuesday is, as you know, Tuesday will be an online lecture day. So I'm going to send you Tuesday's Microsoft Teams invitation via email. So you're going to receive that anyways. But the Tuesday, 9 a.m., you're going to turn in homework assignments of 1B. 8 programs. Okay, so if you wait until Monday night, it's going to be a disaster. I don't think you can complete 8 programs overnight. It's impossible. I can safely say that. I can probably do it, but I'm not sure. I mean, 8 programs overnight, probably okay, but I don't want to do that, at least, okay? So I would probably pick up 1 hour a day, maybe 30 minutes a day. You know, it's fine. 1 program at a time, steady pace, okay? Starting with your notes, because your note is where you get started. You're going to look at example problem we covered in class. We look at the lectures before we hit example problem. Everything is given in your notes. So let's get started from the notes. And then hopefully your homework solution should make sense. And then after that, that's your own solution. You're going to download those worksheets. And then you're going to try to explain what you did to someone else. Someone else means me. If I don't understand, how can I get you partial credit if you're doing something wrong? Now, if you're doing everything perfect, just give me solution numbers, but I still want to know how you get it. If I'm not convinced, I refuse to give you any partial credit. Okay, so that's quite important. I don't want to repeat the same thing over and over. If you choose not to do it, it's your responsibility. Okay, so now, also the quiz. Yeah, I guess it's like a few people almost did perfect. A few people seems like have no clue of what you're doing. Let's fix it. Okay. For those who actually did very poorly, you probably received email this morning. Please respond. Okay, important. Please don't ignore me. Number 1 sign of student ranking the course is just to start to ignore professor's communication attempt. Okay. So please don't ignore me. Just do something. I can talk, of course. I can give you honest advice. Honest advice. I'm not going to write to you because it doesn't work anyway if I write to you. Okay. So, any question about what's going to happen next week? Okay. Having said that, let's just get going with section 2A. Go ahead. Question.
Do you have like a formula sheet on the exam?
No.
Nothing?
Nothing. Usually. If I feel like, hey, this is the equation, I probably, just make sure I give it to you. Of course, I know you know it, but kind of saying that kind of formula is going to be probably included inside of program statement. Or I just give you notes. By the way, notes. This is the equation of equilibrium. Of course, equation of equilibrium we're going to cover today, but summation of force in x, y direction is all 0. Everybody know that kind of equation. So I guess the question is, how can you apply properly? Yes. So formula sheet, usually not. I don't feel this class needs formula sheet. Yeah, if there's an equation that it's kind of hard to remember, I'm going to put it and then integrate inside of the equation, inside of the program statement. Or you can always ask that kind of question during the quiz or exam. Raise your hand saying, hey, Dr. H, I just can't remember equation of circle. You mean pi r squared? Oh, yeah, that's what I want. You can ask Dr. Stuff. No problem. Okay. Suppose if a problem is given, derive this particular equation, and then, hey, Dr. H, give me that particular equation. I can't do that because that's the answer. Obviously, I have to react differently for each time, but you can freely ask that question. I'm not kidding. This actually happened. There's one student taking my aerodynamics class during the final exam, raising hand. I just can't remember the equation of circle. You mean pi r squared? Yeah, yes. That happens. No problem. Okay. Any other question? All right, let's get going. So section 2A, we are going to start talking about statics. What do you mean statics? Do you remember the question? What is the statics? I think we talked about that. This is the statics. What is the statics? You are going to express a system or a mechanical system or some kind. We are going to start with a small tiny particle. Okay, maybe baseball or something here. You apply force here, force there, force there, force there. Everything is in balance. So baseball stays in place. Statics. So equilibrium is something we are going to take a look at it in this class. This is the main subject. So we are going to start with a particle, and then we are going to apply particle on 2D Cartesian, then extend it to 3-dimensional space, Cartesian space. We are going to introduce a moment. Do you know the moment? Moment is, suppose the force is applied right here with this much offset distance, it is going to create the tendency to rotate. Well, I don't want to do that, but rotate. That's called moment. So force times distance create tendency to rotate. That's moment. That's essentially the torque of your drive shaft of your car, the torque. Anyways, so we are going to talk about that. So at that moment, we are going to introduce you vector cross product. Now we already looked at the vector dot product. Now this is also vector cross product. This is sometimes called vector multiplication. Okay? Remember, dot product is a scalar multiplication. Result is a scalar. Cross product is vector multiplication. Result is a vector. So vector cross product against another vector is going to have a vector result. And then that is going to actually resolve certain value in certain direction, how much moment is developed. That's the meaning of cross product. So we are going to take a close look at it. Okay. So let's just begin with next page. Let's begin with a question saying, what is equilibrium? Interesting question. So anybody? What is an equilibrium? Go ahead, Yashan, go ahead.
The forces and moments are imbalanced.
Imbalance, okay. Forces and moments balanced up. As a result, no motion. This is essentially the name implied statics. Okay, so yeah, go ahead.
If a particle in the same velocity all the time, isn't it equilibrium as well?
It's not the static equilibrium, but it's an equilibrium. Yes, you can say that. In other words, you are not accelerating. So constant speed motion stays constant speed. That's also oftentimes called equilibrium, but the statics, we are going to avoid that because dynamics actually starts with that discussion. Yeah, good point. So we are going to restrict ourselves for no motion for this class. So absolutely, we are going to avoid talking about motion, okay? Now, if the motion is involved, even though it is equilibrium, in other words, there's no acceleration, dynamics will cover that, okay? All right, so very simple. Equation of equilibrium is if you sum up all the force vector could be multiple force vectors in lots of different directions and locations. But if you add them up, the result is zero. It's not zero. Zero vector. What do you mean? Summation of all the force vector becomes zero vector. Do you understand this? Zero vector. This is not the scalar zero. If this is a 3D Cartesian space, zero vector means that every single component in all three directions are all zero. That's called zero vector. So that's why we indicate with a vector notation on top of it. This is not the scalar zero. Even though the scalar component in x is zero, if you have a y and z component non-zero value, the vector is not the zero vector. So let's be careful about that. We are going to be, I'm going to be very strict against, vector notation versus scalar notation because those are fundamentally very different meanings. So let's just not confuse up or mix up the usage. So again, important thing is free body diagram shows up. This is one of the key elements, as I kind of emphasize all the time. Free body diagram is somewhere you get started. If you do poor job drawing poor free body diagram, usually that's it. You can do whatever the rest, but I don't care because you do wrong thing anyways. That's free body diagram. It's super important, especially statics and also solid mechanics. Okay. So you have to train up yourself as a good sketcher. You do a really good sketch, have a very accurate free body diagram, your problem is 80% already solved. If you do poor job, you can never solve anything. That's free body diagram. So let's just take a look at, okay, forces acting on a body. That's called free body diagram. We are going to probably spend some time drawing free body diagram, but there are forces developed within the system or mechanical system. A good example is a spring. Okay, so this is the linear spring. Equation of the linear spring is forces developed because of K times S. K is something called spring constant or sometimes called stiffness. This is essentially how much spring force is developed per unit to change the length. S is, of course, amount of changed length of the spring. Okay, so if you pull the spring and then stretch up this 0.2 meter, and then if the spring constant is given, spring constant multiplied by this S is going to give you the magnitude of the force, for example. That's the linear spring. You can compress it, of course. If you compress 0.2 meter, usually indicate negative sign. With the spring constant multiplied, you're going to determine the force developed or force required to compress that much distance. Okay. Next one is, this is very typical for probably for a while. There's a rope you're going to pull. Rope can only develop one type of force, something called tension. Okay. So we oftentimes use the notation T to indicate tension of the rope. Rope cannot be compressed. You can't do that. Now, if you have like a metal bar, you can actually compress or pull. So force could be tensile, could be compressive. Well, this is compressive, tensile or compressive, but rope cannot. So if you see the mechanism with rope, the only type of force you can develop is a tensile, tension. Okay. Okay, and then the direction is, of course, the direction of the rope. So the force developed inside of the rope is in the same direction of the rope, basically. Very simple. Okay. So this is some of the key items of how to draw free body diagrams. Now, there are a few homework assignments and also examples making you to practice drawing free body diagram. Let's just do not underestimate. This is very, very important practice. This is one of the most important key elements of ES201. First of all, draw outlined shape. A body is isolated, free from its surrounding. Free from its surroundings means if a body is connected with certain device, such as pin, bolts, roller, or whatever, you're going to try to disassemble. Make the body isolated from those constraints. And then as you disassemble, remove the bolt and then stuff like that, you're going to replace that with appropriate reaction force, support reactions. You're going to find out those things, okay? And then if the force is applied on the body, of course, you're going to put it with an angle, or could be distributed loading, could be a force is applied at the tip. If so, you have to draw it. If the body comes with its own weight, you're going to find out the center of gravity and apply that weight for that center of gravity. Something like that. So, and also it's quite important to identify both known and unknown forces, because unknown forces are something you want to find out applying equations of equilibrium, okay? So for example, this is a particle. Looks like four forces are acting on it. One of them is pushing, those two forces applied. Those two are forces applied on the other direction. So this is a 2D x and y plane. So you have to identify what is the component of each force in x and y directions. Suppose if you add them all up in x and add them all up in y, you can determine resultant force components in x and y, then add them up to get resultant force. And then you can determine the direction of that resultant force. Isn't that something you did in quiz 1? Right? Did you do it right? I hope so. But if you didn't do it right, please fix it by yourself. Okay? Like I showed you, every time I did something wrong, I did it by myself to make it correction. In other words, for me, it's okay or acceptable to make mistakes. Of course, I'm human, you're human. Okay? But it's not okay if you just don't care. Don't correct any of your mistakes. It's not okay in terms of engineering standard. I'm not going to pass you in this class if you don't do that. Please correct your mistakes all by yourself. In other words, how much your original work you accumulate over the summer? Can you accumulate this much original work? Of course. Right? It's not someone else's work, or it's not a solution posted online by a professor. I tried to memorize it before the exam. That's not the study at all. Study is how much original work you did. And then how much mistake you made is okay. I mean, accept it as long as you correct them all. Okay? Please do that. All right. So equations of equilibrium is going to be applied along with the free body diagram, and basically say some of them are already known by you, some of them are not known. You can determine the unknowns. Suppose this is like 1D, but this is a particle. Force F is applied in this direction. 10 Newton is applied. What is the force F? You can find out this force by applying summation of all the forces in x direction set equal to 0. Hey, F must be minus 10 Newton if you call this particle in equilibrium. Equilibrium means, okay, if you add them up, all the forces, the result is zero vector. That is equilibrium. That's why this particle is not going to move. Okay? All right. So let's just take a look at some examples. Class example 211, page 4. Okay. Determine the magnitude of force F1, F2 so that particle P is in equilibrium. Okay. So I'm going to, of course, start with free body diagram. Okay. So as we construct the free body diagram, of course, you're going to start with a particle P. And I'm going to, first of all, set up the coordinate. I can't do it straight on. But anyway, this is y coordinate, positive. This is negative y direction. This is x coordinate. This is negative. This is a positive x coordinate, x. Okay. And then let's begin with, okay, known force. I'm going to use probably green to indicate known. So 400 pounds. Sorry, I forgot to silence my phone. Okay, so 400 pounds. This force is applied with 30 degrees from here. Okay? And then two unknown forces. Okay, this is, I'm going to switch the color here. One of the unknown forces, F2. This is a vector, okay? Looks like this is 60 degrees. And the other force, F1. Looks like the ratio is given. So ratio of 5 and 3 and 4. Okay? Magnitude, I don't know. So now we are going to apply equations of equilibrium. As you apply the equation of equilibrium, of course, you're going to put the sigma. This is a summation, okay? So what kind of summation are you going to do? You're going to do a force summation. Summation of the force. And now, which direction you are summing the force? X direction. Now, which direction is a positive X? This is the direction of positive X. Okay? So let's use this standard. So I'm going to sum all the forces in X direction. This is the positive X direction coordinate. Okay? And then if this is in equilibrium, this must be 0. This is a scalar. In other words, direction component of X of all the forces must be 0. This is a scalar equation. Okay? So let's just find out all the X direction component forces. Okay. First of all, okay, F1's component of X is this thing. What's this? Magnitude of F1 times what? This thing. What is the magnitude of that?
The angle between that and
No, magnitude.
Well, yeah, but I'm saying the equation.
There's no angle given, but the ratio is given. So whatever the magnitude of F1 here, multiplied by 4/5, isn't it? Do you agree? So this is the magnitude of F1. Okay? What is component force of F1? So this thing is F1 times 4/5. How about this? Anybody? How about this? What's this force? This is F1 times 3/5, correct? That's right. Do you follow that? Okay, so let's just break down everything into X and Y component. Go ahead, question, Ryan?
Okay, so I'm still struggling on why you chose 4/5 for the X direction. And then
Because
4/5
this is X direction.
So,
This is magnitude.
oh, that's X direction. Okay.
That's right. This is
Oh,
X
right,
direction.
okay.
This is X direction.
And 3 is
This
Y
is
direction.
5.
Yeah.
Okay. And how about this? This is 400 times, what is it? Sine or cosine? Which one? Sine 400 sine 30. How about this force? This is 400 cosine 30. Do you follow? This is 400 pounds x direction component. This is 400 pounds y direction component. So this is 400 sine 30. This is 400 cosine 30. Do you follow that? I hope. How about this F2 then? We already did this. Wait a minute. How about this? What's this? Anybody? F2. Is it 60 or cosine? Or sine? Cosine or sine? Which one is it?
It's sine.
Sine. Okay. F2 sine 60. How about this?
F2 cosine 60.
Cosine 60. That's right. So I think it might be a good idea to resolve everything in x and y to begin with, but let's just move on. Go ahead.
So sine 60, even though it's on, the arrow's going on the x-axis, why is it sine instead of cosine? Because doesn't cosine work with x and all that?
No. If this is 30, okay, sorry. This is 60,
Oh, okay.
right? In this case, I can't draw. Sorry about that. In this case, if you get confused, just draw a triangle. This is 60. And then this is F2. This is F2 sine 60. This is F2 sine 60. Is that right? Is that right?
Yeah.
You can sort of change the direction of that, making it like this. Making it like this. Let's say this is 60. This is 90. This is still F2. What's this? F2 cosine 60, right? This is F2 sine 60, right?
Yeah.
Same thing. Yeah, so it's just the same thing.
Gotcha.
You have to kind of rotate and take a look.
Yeah.
All right, anyways. So let's just add them up. So forces of x direction of F1 is, of course, this one. F1, 4/5. This is a positive direction. Let's be careful. How about F2? This is minus because it's negative direction. This is F2 sine 60, right? How about 400 pounds? Again, it's negative. Be careful. 400 sine 30. This must be equal to 0. Okay? This is one of the equation you came up with. Let's just simplify a little bit. This is going to be 0.8 F1 minus 0.866 F2 minus 200 is equal to 0. So you got one equation. Now this equation includes two unknowns. Do you realize it? F1 and F2, two unknowns. So this equation alone cannot solve this problem. You can only get the ratio of F1 and F2. Okay, that's the best you can do. So you need another information. What is it? Of course, you can. Some forces in y direction, and then let's say this is the positive y direction axis. Okay, let's just set it equal to 0. Let's just do the same thing. So now F1's y direction component is this. Okay, be careful, it's negative. Negative F1. So this is F1. Okay, so this thing is negative y direction. So negative f1, 3/5, right? What else? F2 is this thing, again, negative. Negative f2 sine of 60. Is that right? 400 times y direction component is positive. This is 400 cosine 30. Let's just set equal to 0. This is the second equation you come up with by summing all the forces in y direction. Let's just simplify a little bit more. This is going to be minus 0.6 F1 minus 0.5 F2 plus 346.41 is equal to 0. Oh, you got the second equation with also two unknowns, F1 and F2 coming up. So now you have equation 1 and equation 2. So now you have to do solving these simultaneously. Can you do such a thing? Can you do such a thing? So let's just try. I wait for you, but just try to find out F1, F2. Because when I prepare this solution, I use software. I'm no longer using two simultaneous equations, two unknowns. Do you know how to do this? Let's just challenge yourself, because you have to probably do this for your next quiz. Go ahead and do that, each person. Find out if you can do this kind of solution. And then, of course, I welcome Braden to basically join in and give the result. Can you get the value? Please, everybody, participate. If you want to get good grade on next quiz, do it. Get busy. taking way too much time. I give you answers just to finish up by yourself. But unless you have this skill set, you're not going to pass next quiz. Okay? This is the two equations with two unknowns, simultaneous solution. Taking way too much time for you guys to solve. Please brush up your memories. You can do this better. Okay, so those are the answers. Please work it by yourself at home. Okay, guaranteed this kind of thing will show up on next quiz. If you cannot solve it within a given time, you're not gonna pass this class. Sorry. Okay, pick up that kind of skill. This is not math class. I'm not gonna teach you how to do it. All right, let's move on. So this is the homework. 211, determine the magnitude and the angle theta of F1 so that particle P is in equilibrium. Essentially the same kind of problem. So please do it right after today. I mean it, right after today. You actually start working on those problems. Do not throw into last minute. Okay? All right, next page. Class example 212. Let's just take a look at another one. Okay? Determine the force in cables A, B, and AC necessary to support the 12 kilogram traffic light. First of all, what do you mean 12 kilogram? Oh, you guys didn't you take the quiz? Go ahead, yes, Sean.
Talking about the mass of the.
Is this mass?
Yeah.
Is this mass? Really? So this is 12 kilogram mass?
Yes.
Anybody else?
Yeah.
You go with, oh, this is mass.
It
Yeah.
specifies, so I think it's mass.
Yeah, it's mass.
It doesn't specify it's a mass or not the mass. Program doesn't say anything about it. Is this mass? Oh my goodness.
Because force, you would say
Eh?
12 kilogram force.
Oh, you're saying this is a force?
No, this is a mass.
This is a mass? So this is a 12 kilogram mass, you say? Okay, go ahead.
Is it force when they use the notation?
Oh, this is a force if it's a notation of newtons. Can you convert kilogram into newtons?
It's
One is mass, one is force. You cannot convert those two. Wait a minute, didn't you take a quiz? So who actually takes it as a 12 kilogram mass? Raise your hand. One person, two persons, three people, four people, five, huh? Actually, how many people actually take this as a 12 kilogram, but this is a force or weight? Nobody? Oh, I'll take it. Then you're going, oh my goodness, professor's taking that one. I'll take it. Either way, it's fine, right? You know what I'm talking about? This is on us. 12 kilogram of traffic light has a weight of 12 kilogram force. So you can interpret. If you take it as a mass, okay? If so, this is a mass, right? So you have to figure out what is the weight. Weight is mass times gravity. So let's just do that, 12 kilogram. Multiplied by G is 9.81 meter per second square. How much?
117.72.
117.17. Is that right?
72.
172, sorry, 172.
No, 117.72.
72. What's the unit?
Newton.
Newton. Let's convert it to kilogram force. Okay. 1 kgf is 9.81 newtons. How much kilogram force do you have? 12 kilogram force. That's right. So either you can take mass 12 kilogram and then use the Newton value as a standard unit, you can do that, of course. Or, hey, this is 12 kilogram force, so I'm going to use the value 12, but knowing this is a kilogram force as a unit, but not standard. It's not standard. Okay. So I think it's a good idea to probably stick with this because this is a standard unit of weight or force. So this 12 kilogram traffic light, this is actually 117.72 Newton. As an engineer, I think it's very healthy to use the standard unit. So let's use unit of standard, Newton. But suppose if you pick up a 12 and then knowingly using 12 as a kilogram force, because we are adding force, not the mass, I'll give you full credit too. But you have to be very careful because you intentionally pick up the non-standard unit in your calculation. So oftentimes, if you use that value against other standard units such as feet, slag, and other things, well, no, it's not. That's SI. 12 kilogram force cannot be used against mass of kilogram or meters or anything because it's non-standard unit. But as an indication purpose, you can use that. That's fine. So again, units are important. This class probably not going to put too much emphasis on units, but if you start taking fluid mechanics, if you don't know this kind of thing, the professor gets so super mad. Guess who's going to teach fluids? I don't know. Maybe me. I'm not sure, but I'm not going to totally mix up kilogram force and kilogram mass. It's a big no-no in engineering. So it's safe to stick with this because it's standard. Okay, so I'm going to draw a free body diagram to begin with. Okay, so let's just draw it. So this is a traffic light. Here we go. This one has a weight W. This is going to be basically 117.72 Newton. Okay, going downwards. So vector notation wise, this is like Y, right? Okay, sorry. This is J. W equal to, yeah, it's okay. Sorry. I'm going to do just a simply W. Okay, just a simply W is 117.72 Newton, direction going down. Okay, so let's just draw a coordinate. This is the coordinate. No. Because traffic light is, yeah, this is one of those cheap ones, right? Cheap traffic lights. You know, it's like a suspended wire kind of traffic lights. Okay, anyways, this is X coordinate, this is Y direction coordinate, Y and X. And obviously, two forces is going to support, right? Wire or cable AC, cable AB supports it. So to the direction of cable AB, you are going to have a force developed, only tension. So let's use this tension T, and then direction A to B, right? So this is AB. Direction A to B, A to B. And the other side, of course, the angle is given here. Angle is 12 degrees. Okay. The other side is, of course, probably similar manner. You have other cable. This is the cable AC. Tension is developed, TAC. The direction. This is a 2, 24, 25. Those are the ratio given. Okay. This is TAB because this is A to B. A to B, okay? So this is TAC because it's A to C. Before we move on, I think, no, I think it's okay. Yeah, it's okay. All right. Okay, so far. So this is a sketch. Okay. So obviously, those two forces have a component. Let's just figure out the component because that's more convenient. So component of X and Y direction. Okay. What's this? And what's that? What's this? Anybody? What's this force? Magnitude?
F time cosine.
Cosine TAB times cosine 12. You follow? How about this? TAB sine 12. Correct. All right. Let's do the same thing for the other side. Okay. So two components. This. No, don't do that. So, okay, two components. Sorry. This and that. What's that?
TAC times 24 over 25.
This is going to be 24 over 25. That's right. Do you follow that? Everybody follow? 24 over 25. Okay. How about this? 2 over 25. That's right. So those are the all components of each direction. So let's just now apply summation of forces in each direction. Okay. So equations of equilibrium. Equations of equilibrium. First of all, let's just add all the forces in x direction. This is the positive direction of x. Let's set equal to 0. If it's equilibrium, this should happen. Okay. So obviously, okay. So this is a TAB cosine 12. Positive x direction. Yes. How about this? This is a negative x direction, so it's negative TAC times 24 over 25. Those two added up, it's equal to 0. It's just to simplify a little bit, 0.9781 TAB minus 0.96 TAC is equal to 0. So this is equation 1. Well, two unknowns, TAB, TAC. Let's do the summation of the force in y direction, set equal to 0. So y direction. Don't forget the W though, okay? Now, this is a weight in y direction. So this force, this is a positive y, TAB, sine 12. And this force, this is also positive. This is a positive TAC, 2 over 25. Don't forget the weight. Weight is a negative y direction, so negative 117.72 Newton. All of them added together should be equal to 0. So simplify a little bit. This is going to be 0.2079 TAB plus 0.08 TAC minus 117.72 Newton is equal to 0. So this is the second equation we just picked up. So now again, this is two equations with two unknowns, TAB and TAC. So let's just try to solve it. I'll wait for you this time. How much time does it take to solve this kind of simultaneous equation? Just go ahead, do your best. I wait for you. Just do your best. Next quiz, you have to do this anyways. It's just do it. Don't you have like a calculator with a simultaneous equation solver or something? If so, find out how to use it. Now is the time. If you don't have such a thing, just to pick up a piece of paper, just do arithmetic and find out two unknowns. I wait for you. Everybody do it.
Takes a lot less time on the calculator.
That's right. Go ahead, give me a number.
Got that AD is 336.8.
No. No. Six.
F1 is 400 Newton.
400? What?
Newton.
400 Newton. About 400?
Yeah.
Exact 400?
399.
You're talking about AB?
Yeah.
Really?
I did a mistake here.
Too bad, huh?
I got about.
Yeah, you got what?
414.
440. That's AC?
Or AC.
AC, okay, 414. 43, correct. How about AB?
I got 406.76.
406.76, correct. So it took about, a minute and 40 seconds. Not bad. I wait for others' confirmation. Just continue doing it until you get those numbers.
Yeah, you got the 4.
You got the result. I'm gonna wait until everybody says something.
For AB, I got 407.33.
0.33, fairly close, but yeah, I guess it could be probably just a round off. Yeah, it could be round off. I can take that, no problem.
I can confirm it.
You confirm it, great. Thank you, Brayden.
Yeah, me too. I think I just used different numbers for the original
But
question.
the very close number, right? Okay, good.
Yeah.
Good. That's possibly round up. So here's a check to yourself. In other words, you can't lie to me. This is engineering classroom. If you cannot solve this kind of equation, you can't pass this class. Please do it. You got to do this in next quiz anyways. Okay, so make sure, okay, suppose if your calculator supports simultaneous solution function just to find out, look at manual, set it up so that you can punch those numbers and get, results out. I'm actually using software, so I don't use calculator nowadays. I don't have one. Okay. Question here. Any question? This is not math class, so you can, of course, you can do this. All right. So this is a homework 212, next page, page 7. Okay. This is again, this is going to make you draw free body diagram. Do you realize that I'm doing free body diagram. This is the traffic light with the weight of this much Newton. Coordinate is set, two forces applied. This is a cable ABAC. Now, follow the standard notation. If I say tension AB, that means this is the force, tensile force, direction-wise, from A to B. That's why it's AB. This is a tensile force from A to C. That's why TAC. If it's opposite, I may end up calling BA or CA. There's a reason for it. So this is going to indicate the direction. Okay, so it's just to follow standard notation. So I guess important thing about this homework is you have to draw free body diagram very accurately. If you don't do that, I guess the solution is essentially meaningless. Okay, wrong free body diagram is that's it, you're done. Okay, don't underestimate. Also, another homework here. Homework 213. Here we go again. The 30-kilogram pipe is supported by a system of 5 codes. Determine the force in each code for equilibrium. Is this 30-kilogram mass or 30-kilogram force? Which one is it? I don't care. You can take either way, but if you take it as a force, consistently use KGF. This is required. If you take it as a force. If you don't like it, convert it to Newton. That's fine, because Newton is standard. You don't have to worry anything about it. You can use kilogram force, that's fine. If you take it as a mass, of course, you're going to automatically multiply by 9.81, make it Newton. That's what we did in traffic light. That's fine too. Either way. Be consistent, that's what it is. Okay. All right. So, yeah, I think I did this solution recently. What did I do? Well, free body diagram of this section. Next is free body diagram of this ring A. Ring A has 1, 2, 3 forces acting on it. So this is another free body diagram. And then another free body diagram of ring B. This ring B supports 1, 2, 3 tension forces. So I ended up drawing 3 free body diagrams, solving one after another. That's what I did. Okay? Because every single code, you have to find the force developed inside. So you need probably at least 3 free body diagrams. Okay? Does it make sense? Don't be lazy, okay? Free body diagram is quite important to solve this problem. And then you should start today. Don't wait until, I don't know, when is the next homework due? I don't know. Do you think you can retain today's memory? I don't think so. Next page, let's just take a look at the 3-dimensional force systems. Now we are going to extend from 2D to 3D Cartesian. Now the sketch becomes more complicated, challenging. So you may end up spending more time drawing more accurate sketch in 3D. And then 3D sketch involves recognition of planes. Recognition of planes. So when you draw a sketch of 3-dimensional Cartesian coordinate, this is a free body diagram of a single particle, right? Now, when you draw such a thing, first of all, X, Y, and Z coordinate direction is specified, and then you're going to create 3 planes. This plane, this is called XY plane. You're going to draw a XY plane figure. So if you project F3 to the XY plane, this is the F3's XY plane component, right? So this is F3 projected down to XY plane. So on XY plane, you have this much component of F3. That F3 can be resolved into 2 components, which is Y and X. So this is F3 X. This is F3 Y. F3X and F3Y gets you this. F3 projected component on XY plane. Then that one added together with added together with this, okay? This is F3Z. So you can dissolve F3 into three components, F3X, F3Y, F3Z. It's not easy doing such a thing, okay? So you have to basically always think about, okay, so this is the plane that if I project this force into this plane, this is the projected force onto this plane. You can dissolve then into two direction components of that particular plane, usually XY. Okay. So sketch is quite important. If you do inaccurate drawing, it is going to screw up really easily. So spend some time, do free body diagram to begin with. And then the rest is the same thing because this is three-dimensional. You're going to sum forces on all X direction, Y direction, Z direction, X, Y, Z. Okay? This is the equation of equilibrium. Equations of equilibrium are applied on free body diagrams for 3D space. First of all, Cartesian coordinate system X, Y, Z must be come up, okay? And then label all known and unknown forces. Apply equations of equilibrium. Let's just take a look at next page. Plus example 221. Oh my goodness. Determine the magnitude of F1, F2, and F3 for equilibrium of the particle. So I'm going to once again sketch this particle. Okay. So particle is here, and I'm going to draw coordinate. This is a Z coordinate. This is the Y coordinate. Again, right hand coordinate. This is X coordinate. And then the important thing is I'm going to draw force, okay? Force F1. So force F1 looks like, okay? So I'm going to stretch out X in negative direction coordinate. So force F1 is going to be projected onto X and Y. So this is force F1. Force F1 is on XY plane, looks right. Yeah. This is on XY plane. How about the other forces? Force F2 is straight up in Z direction, isn't it? This is F2. Force F3. Okay, force F3 is, oh my goodness, I hate this to do, but anyway, so this is force F3. So I'm going to, again, stretch out the Y coordinate in negative direction. Then draw a line like this. And then looks like this is 45 degrees. So let's say this is XY plane. Once again, this is XY plane. This is 30 degrees. So it looks like F3 is also on XY plane. Okay? 200 newtons is straight down, looks like. This is the 200 Newton. 400 Newton is in just basically positive X direction, 400 Newtons. Okay. So this is a sketch, the best sketch I had using digital device. Like I said, I hate the digital device doing such a thing, but with a piece of paper with straight edge, you can do better job than this. So let's just apply equations of equilibrium. Okay, so I'm going to do summation of force in X direction set equal to 0. Now, X is this direction is X, okay? So I'm going to do that. So first of all, 400 Newton force is in X direction. That's right, this one. What else? F1's X direction component is that. What is it? It's a negative. What's this?
Sine 30?
This is a sine 30, that's correct. F1 sine 30 degrees. And also F2's, no, this is F3. F3's X direction component, which is this. Or this, either way. What is that then?
3 sine 45.
This is the F3 sine 45. It's positive or negative? Negative. F3 sine 45. That's it, right? Set equal to 0. Let's just simplify a little bit. This is minus 0.5 F1 minus 0.707 F2, no, F3 plus 400 equal to 0. So this is equation 1 you got. Okay, let's just do the summation of the force in y direction. Y direction is this way. Let's just set equal to 0. So y direction, you have force F1, this much force, y direction, positive. What is that?
1 cosine 30.
F1 cosine 30, that's right. F3's y direction component is this much. This is negative. How much? F3, negative F3 cosine 45. That's right. That's it, right? It's equal to 0. So if you simplify, this is 0.866 F1 minus 0.703 F3 is equal to 0. That's right. Equation 2. All right. How about summation of the force in z direction? Z direction is this much. This direction is c. It's just a set equal to 0. Okay. Oops, 5 more minutes. Okay. So F direction, there, well, Z direction, there are quite a few. F2. F2 is straight up positive Z direction, and then negative 200 Newton. That's it. That's it, right? Oh, this actually gives you a single answer, right? F2 is equal to 200 Newton. That's right. So, oh, you got one. This actually creates chain reaction, isn't it? So this equation, if you, no, you can't. You still need to solve 1 and 2, okay? Solving equation 1 and 2. Of course, you can do that. So equation 1 and 2 simultaneously solved, like you did in the previous example problem. You can get F1 and F3. Please do the math by yourself, but F1 should be 292.83 Newton. F3, 358.68 Newton. Okay? Do the math by yourself. Any question? Let's stop here today. Any question? Okay, so coming back, well, looks like homework 221 is assigned here, page 11. So coming back next week, Tuesday, online, we are going to pick up from page 12, class example 222, and then we're going to probably finish up 2A on Tuesday. So have a great weekend, okay? And then important thing, continue working your homework assignments as I cover my notes. Please do not leave it in the last minute. If you do that, this is summertime, I can almost guarantee you can never pass this class. So please do work one at a time. If you have a question, please send me text. I'll be happy to chat with you if you have any question, okay? So see you back next Tuesday. Have a good weekend. And Braden, have a good weekend. Hopefully see you next Tuesday's on that, so you're gonna be there, but hopefully you recover soon.